Step 7, describing segments. Now we want to look at which tests we could run to compare a metric variable as a descriptor variable over segments. And here we use the obligation score we have in our data set. And the first thing we are doing is we calculate the mean obligation values for each of the segments. And we do this using function tapply. Tapply takes as first argument that a vector, which is split by the second argument, and then this function is applied to each of the splitted vectors. So we're splitting moral obligation into 6 subvectors. On each subvector we apply the function mean, thus that this returns a vector which contains the mean obligation values by segment. Let's have a look at results. So it's a named vector of length 6, and we can, for example, see here segment 6 has the highest moral obligation values compared to the others. If we now want to test if they're significantly different, so we want to test the null hypothesis, all moral obligation means are the same in the 6 segments versus at least one differs, we can do this using, for example, the analysis of variance. And this is performed now using function AOV. We specify the model, so which variable, that's our metric variable obligation, we want to split tilde by that categorical variable C6 by segment membership. And this is the formula will be evaluated using that data frame. So this calculates the analysis of variance and returns an object, and this has a summary method. So we can look at the summary method for that object, and we can see why it's called analysis of variance, because it splits the total variance in our data into a variance which is due to the categorical variable, which is due to differences in mean values between segments, and the remaining variance we have. So that's we have the between segment variance and the within segment variance, sort of. These are corrected for the degrees of freedom we have in our data set, and then we calculate the F value. That's the test statistic for our hypothesis test by taking the ratio of the mean square values. And the F statistic under the null hypothesis follows an F distribution with these degrees of freedom here. And here we can see we get a p-value which is very small. So testing at the 5% significance level, we would reject the null hypothesis that the mean values are the same. So this tells us that there is a difference in mean values. And the next question would be, how do segments differ? So is there just one segment which is different from all the others, or can we tell anything more? And this could be investigated also in different ways. So one thing could be, we could look at the 2K HSD. That's the honest significant differences by 2K. So what does this do? It calculates all pairwise differences between all segments. So we're interested in segment 6 different from segment 1, segment 6 different from segment 2, and so on and so forth. So all these comparisons are run, and confidence intervals are calculated, and they're calculated in a way that we ensure that they overlap with 0 in 95% of the cases if the null hypothesis is true. So we would say we reject the null hypothesis, that they're all the same if at least one confidence interval doesn't overlap, and because we're likely running a lot of simultaneous tests, we need to correct for this to get the right rejection rate. So let's plot these results. So this is telling us that we have corrected for multiple testing, and we see, okay, not all are overlapping with 0, so we have a significant difference between segments, and we can, for example, see here that segment 2 and segment 1, here we have an overlap with 0. They are not significantly different in their mean values of moral obligation, whereas here the comparison segment 6 versus segment 1 indicates that segment 6 has a higher, significantly higher mean or moral obligation values. Alternatively to the 2K thing, we could also look at pairwise t-test. So the function pairwise.t.test calculates for that variable for each of two levels of that factor comparison. So this is the categorical variable which can take two or more levels, and then we are looking at all pairwise differences. And let's look at the result. The result just tells us which test were we running, what data were we using, and then we have here the matrix of p-values for the pairwise test. So this is the test is the mean value in segment 1 and segment 2 the same, and these p-values have been also adjusted for multiple testing using a method called Holm. So we see segment 1 and segment 2 don't differ in their mean moral obligation values, whereas for example, segment 6 and segment 1 significantly differ. So this is a very compact way of telling are two segments the same, yes or no, in their mean moral obligation values. However, what we don't see is in which direction does it go. We see segment 6 and segment 1 are different, but we don't know is it because segment 6 has higher or because it has lower values. And we would need to go, for example, back to the parallel box plot to assess this. Alternatively, we can also look at the same results for age. So now we're just calculating the mean age values. We see that in segment 6 the oldest are, whereas in segment 5 the youngest are on average. And we can run that f-test again with the summary on the analysis of variance. And also here we would reject the null hypothesis that the mean age value in all segments is the same.